methods, more sometimes really procedure within while minutes or while seconds. I will be live with you so that will be benefited from applying the theorem of Murad Sultan's video. Okay, so prepare yourself. Okay, drink your cafe and stand in your chair and let the desk in front of you. And we will start now using my theorem to solve for 40-degree formal equation, not the second degree, not the third, not the fourth, not the fifth. So here is how to apply the theorem, okay, to let's say to find the exact sample roots where approximation method and Abel's method and Nisak-Newton method and Calvin method, all of them fail. Okay, to obtain or to give you extremely just equations. Okay, that's not that doesn't satisfy the equation. It is a 14 equation. Okay, so I will share now the screen with you. Okay, on my screen. Okay, we start with all this is our 14-degree formal equation.
Okay, let's unpack this. We're diving into a corner of mathematics that, well, it often brings us face to face with limits.
Absolutely. Solving polynomial equations.
Yeah, exactly. High degree ones. We all learned the quadratic formula, maybe wrestled with cubics, quartics.
But beyond degree 4, things get tricky. Classical algebra kind of hits a wall.
Right. You hear about Abel's theorem suggesting, no general solution using simple radicals for degree 5 and up.
That's the standard picture. So for those higher degrees, you're often looking at approximations.
Numbers that are close, but maybe not exact, and potentially carrying errors.
Precisely. Numerical methods like Newton's method, they get you close, but it's not the symbolic perfect answer. Or the theory says a neat solution might not even exist in that radical form.
But the material you shared with us for this deep dive, it seems to propose a completely different path.
It does. It introduces something called Ezouidi's theorem.
And the claim is, well, that's pretty bold, finding exact symbolic solutions, even for complex, high degree polynomials.
That's the promise. So, our mission today is to dig into these sources you send, understand how this theorem supposedly works, and how it claims to bypass those traditional roadblocks.
Avoiding approximation, getting the actual mathematical form of the roots.
Exactly.
Yes,
And the sources use a really challenging example to demonstrate.
They
exactly.
really do. We're talking about a polynomial of degree 14. Just saying degree 14, it feels, well, daunting.
It's significant. The source material lays out the specific equation. It starts x iota a, then minus 14 my air plus 91x.
Yeah, we probably don't need to read all 15 terms right now, but trust us, it's long and the coefficient.
Here you can see my colleagues. This is a 14-degree formal equation. Let's begin by examining the formal equation we are working with. Here is our degree 14 polynomial. Okay, x is to the power 14 minus 14 x is to the power 13 plus 91 x is to the power 12 minus 364 x is to the power 11 plus 1001 x is to the power 10 minus 2002 x is to the power 9 plus 3003 x is to the power 8 minus 452 x is to the power 7 minus 17,997 x raised to the power 6 in up to 1. Okay, last option is 1. Okay, let's see it. Continue. Okay.
get pretty large.
They do. But what's crucial is how the source expresses this polynomial. It uses a specific notation for the coefficients.
Ah, right, the LRQ
Yeah,
notation.
it's not just renaming, it seems to be setting it up in a format that the theorem works with directly.
Okay, and the source lists these specific values.
It does. It gives L0Q is 14, L1Q is 91, L2Q is 364, and so on, all the way through L13Q, which is a large positive number, 2,247,001.
So these are the specific ingredients for this particular degree 14 polynomial.
The exact coefficients that define it.
So we have this beast of an equation defined by these L coefficients. How does Ezouidi's theorem actually start processing these ingredients to find the roots?
Well, the core mechanism described is recursive. It involves calculating a new set of symbolic coefficients.
Symbolic coefficients, not numerical values yet.
Not yet. These are often called L's coefficients, or sometimes L1Q in
Yeah.
the notation, and they're derived directly from the original L coefficients.
Okay, so there's a formula involved.
There is. The source shows a general formula. It looks quite complex, involves sums, combinations, powers of coefficients.
Right.
But the key takeaway isn't necessarily dissecting that formula right now. It's that the calculation itself is done symbolically.
Meaning we're not plugging in numbers and getting an approximate result.
Exactly. It's about manipulating the mathematical relationships between the coefficients to derive these values perfectly, mathematically precisely.
Okay, so it's a transformation based on the polynomial's inherent structure. And the source actually does this calculation for our degree 14 example.
Yes, it applies this process to the specific Illiguln coefficients we listed earlier. And this is where the demonstration gets, well, really striking.
How so? What happens when they calculate these Illigul's coefficients?
A really dramatic simplification occurs. The source documents that after performing these symbolic calculations for this specific polynomial,
Yeah.
a large number of these resulting Illiguln coefficients turn out to be exactly zero.
Zero, like completely gone. For a degree 14 polynomial, you'd expect what, maybe 14 of these things?
You would. But the source explicitly states that S0, S1, S2, S3, S4,
Yeah.
then skipping a couple, S7, S8, S9, S10, S11, and S12, they all calculate out to zero.
That's surprising. Almost feels too convenient. What's the significance of them all collapsing to zero like that?
Well, that seems to be where the power of the theorem shines, at least in this example. By transforming the polynomial using this method, the specific structure of this polynomial is revealed.
And that structure leads to cancellation.
Essentially, yes. When you express the polynomial in terms of these as coefficients, most of the terms just vanish because their corresponding as coefficient is zero.
So it cleans things up massively. Out of all those potential as coefficients, how many are actually left? Which ones are non-zero?
According to the source, just 2 remain non-zero for this specific case.
Only 2. Which ones?
They identify S6, which they calculate as minus 3,000 times 14 raised to the power of 7.
Okay, a specific symbolic value. And the other?
And S13, which is calculated as positive 2,250,000 times 14 raised to the power of 14.
Wow, huge numbers, but crucially, they're exact symbolic expressions. So what happens to the polynomial equation itself when you rewrite it using these S values, and only S6 and S13 are non-zero?
It simplifies incredibly. The general form, which could have many terms involving different powers of x and s coefficients,
Yeah.
it boils down to just the terms involving the non-zero S6 and S13. The source shows it becomes Px Sx S die plus S13 equals 0.
Okay, wait. Let me substitute those values back in. So xos minus 3,000 times 14 arrows times xa plus 2,250,000 times 14 euros equals 0.
Right. Or rewriting slightly.
I see it. X exos plus 3,000 echo 14 euros at 14 equals 0.
Exactly. Look closely at that equation.
It's a quadratic equation.
It is, but notice the variable.
The variable isn't x, it's xa.
Precisely. The entire complicated degree 14 polynomial through this S coefficient process has been transformed into a simple quadratic equation where the unknown is x.
That's quite a transformation. And quadratic equations, we know how to solve those exactly using the quadratic formula.
We do. The source proceeds to solve this quadratic, not for x, but for the term xa. They mention a calculation, sort of like finding the discriminant for this specific quadratic.
And what do they find?
They find that this discriminant-like value for the quadratic in xa is 0.
Zero discriminant. That's always a nice result in quadratic.
It means there's exactly one unique solution for the variable. And in this case, the variable is x.
So there's only one possible value for xa that satisfies this simplified equation.
According to the source, yes. And they find that single value is x equals 8, 1500 by 14. Again, an exact symbolic value.
Okay, we've got xe equals this specific negative number. So the final step to get the roots, the x values of our original degree 14 polynomial,
is to find the seventh roots of this value. We need to find the complex numbers x such that when you raise them to the power of 7, you get 1514 here.
And finding roots of a complex number or even a real number like this one, we have standard methods for that using complex numbers.
Yes, exactly. The source provides the general formula for these roots using complex exponentials, which is standard.
Right. They state it as xkr 1514 x times 17 times e to book 7.
Where k takes integer values from 0 up to 6.
So k0, 1, 2, 3, 4, 5, 6. Each value of k gives us one of the 7 distinct roots.
That's right. 7 distinct complex roots derived directly from the exact value of x.
And the crucial point here, again, is that these are exact symbolic roots.
Absolutely. We haven't used any iterative numerical methods that just get closer and closer. The method, as demonstrated here, has produced the precise mathematical expressions for these roots. No approximation involved in finding these specific 7 roots.
This really highlights how Ezouidi's theorem, or at least its application in this specific example from the source, seems to navigate around the kind of limitations suggested by classical results, like Abel's theorem, at least for certain types of polynomials.
It appears to reveal a structure within this particular polynomial that allows for this kind of exact solution, where maybe we wouldn't typically expect one based on degree alone.
Now, it is worth remembering, as the source itself notes elsewhere, the original polynomial was degree 14, so we'd expect 14 roots in total over the complex numbers.
Correct. This derivation focused on the 7 roots that emerged from solving that quadratic in xe.
The source does also mention, I think, that x1 is a root with multiplicity 2 for this polynomial.
Yes, it does mention that earlier on. So that accounts for 2 more roots. The main demonstration, however...
So here, our 14th differential equation, we found the 14th x roots of this new 14th differential equation. So now I'm going to solve this. I will write alpha subscript k from 0 to 6 is equal to L0, which is 14, plus this one divided by 14, okay? And I will obtain my 14th exact simple roots like that. And which are, in fact, has a multiplicity of 2, means I will write alpha subscript k from 0 to 6 is equal to 14 divided by 14 is 1, and 14 times 1500 raised to the power 1 over 7 exponential to k plus 1 divided by 7 over 14. The 14 will be cancelled. It will be only this term, okay? And you can see this one is a double root, okay? For each, when k equals 0, for example, I obtain a double root. When k equals 1, I obtain a double root also, okay?
Really hinges on using the S coefficients to find that set of 7 roots derived from xe.
Which is still a remarkable feat, finding 7 exact roots for a degree 14 polynomial this way.
It certainly showcases the potential power of the method, transforming the problem into something solvable exactly.
Okay, so let's just quickly recap this for you, the listener. We started with this big challenge, high degree polynomials. Often we hit limits, get approximations, or here they're unsolvable by simple formulas.
Then we looked at the sources you provided on Ezouidi's theorem, which proposes a different approach, aiming for exact symbolic solutions.
We walked through this specific, quite complex degree 14 example.
We saw how the method uses the initial coefficients, the EL coefficients, to calculate a new set of symbolic coefficients.
And for this particular polynomial, a whole bunch of those ES coefficients turned out to be 0.
Which was key. It simplified the polynomial equation dramatically.
Right down to a basic quadratic equation, but where the variable was x.
Solving that quadratic gave an exact value for x.
And from that, taking the 7th roots, we got formulas for 7 distinct exact symbolic roots of the original polynomial using complex exponentials.
A process that bypassed numerical approximation for these roots entirely.
So why does this matter to you? Well, whether you're in science, engineering, finance, or just fascinated by math, the difference between knowing about a solution, having an estimate,
and having the exact symbolic answer can be huge. It offers a deeper level understanding and precision.
This demonstration, as shown in the sources, suggests that maybe some problems we thought were confined to approximation might have exact answers accessible through different mathematical tools.
It reveals a kind of hidden structure, perhaps, that numerical methods might obscure.
Absolutely. It definitely leaves you thinking, how often do we accept limits based on the tools we currently have? Discovering a new mathematical approach, like this theorem seems to be, well, it can potentially reshape our understanding of what's solvable, what's truly knowable in complex systems. What other intricate problems might just be waiting for the right key, the right transformation to unlock the exact solutions?
Okay, here my colleagues, we just solved 14-digit equation using my own theorem. And you can see that the roots are derived recursively while we solve for them step by step. This formula breaks down the polynomial into manageable components, allowing also us to derive exact sum of values instead of approximation. And notice here, because of the recursive structure in Ezouidi theorem, we were able to derive these roots, okay, systematically and precisely without any approximations. Means here in our example, we don't approximate, we give symbolic exact roots, okay, and we vanish it if we want to vanish all the coefficients. Also, the formula works. Okay, thank you for watching, and we hope that you have been benefited. Thank you and goodbye.